Hello everyone, welcome to the biggest ideas in the universe. I'm your host, John Carroll. This is idea number 18, and we are continuing to sort of build back up the universe of our everyday experience from these fundamental ideas that we've been talking about. So the ideas we've been talking about so far often go under the rubric of fundamental or elementary physics. And that doesn't mean fundamental in the sense of more important or more interesting or worth more money or anything like that. It just means that the stuff we've been talking about makes up the stuff of our everyday life. It's sensible to say that protons and neutrons are made of quarks, that atoms are made of electrons and protons and neutrons, but it doesn't make sense to say that protons and neutrons are made of atoms. That just wouldn't be true. So the fundamental physics we've been talking about so far is sort of the base level stuff, and then you put it together to make bigger things. And it turns out that in the process of making bigger things, a lot of incredibly cool stuff happens. It's not always personally my area of expertise, so I can't do it justice as well as some other people might, but there are some very clear big ideas worth talking about in that journey back to our everyday world. And today's big idea is atoms. Now, atoms might sound a little down to earth. You might feel like, well, I know about atoms. I don't need to watch this one, right? You might not know about the spin statistics theorem or gauge theory, but you know about the little picture with the protons and the neutrons and all the electrons going around it. I'm using the catch-all word atoms, as usual, to describe some deeper things. What I want to describe is how you start with the rules of the standard model of particle physics, or really the core theory that also has gravity in it, and how you end up with the stuff that actually makes up you and me. Why these particular atoms? So I'm not necessarily telling you what an atom is and expecting you to be surprised. I'm explaining why atoms are that way. So where we really start is with the standard model of particle physics. And I'm just going to call it the standard model, even though I'm including gravity for reasons which we've already talked about. And you know that what's in the standard model are fermions, which make up the matter particles, okay? And fermions come in two different classes. They are quarks. Wow, it just left my mind there for a minute. Quarks, the quarks which are colored, they have red, green, or blue colors, and they're subject to the strong nuclear force, quantum chromodynamics pushing around the colors. And then leptons, which are just particles that are fermions and do not feel the strong nuclear force. Both the quarks and the leptons feel the weak nuclear force, they feel gravity, most of them feel electromagnetism, and so forth. So you have the fermions, and then you have the bosons, and the bosons also come into very different classes. There are the gauge bosons, the sort of traditional force-carrying bosons. For the electromagnetic force, we have the photons. For the strong force, we have the gluons. For gravity, we have gravitons. And for the weak force, there are the W and Z bosons. And then there's the Higgs boson. And, in some sense, the Higgs carries a force, but it's incredibly tiny, short-range, very weak force, so you don't notice it all the time. But it's a boson, but it's not a gauge boson. It is a spin-zero scalar boson. The Higgs is responsible for the symmetry breaking and the weak interactions that we've talked about before. But it's definitely there. We discovered it. I wrote a book about it. You can read the book. So we'll definitely include it in the standard model. Lots of people have tried to figure out fun geometric ways to present to you what are all the particles in the standard model. I think they are all kind of artificial looking, a little bit ad hoc. So I'm just going to make a little plot. And the plot will be mass of the individual particles. And on the horizontal axis, we will have the charge of the particles, okay? The electrical charge. Different ways to do it, but I think electric charge is very noticeable there. And let's, talk about what we call matter particles. There's also antimatter particles. We'll get to those in a minute, but basically there's just for most of these matter particles, there's also an antimatter particle. So we'll list the charges that we have as -1, like the electron. There are ones that are -1/3, like the down quark. There are particles that are charged 0, and there are particles that are charged 2/3, +2/3. So these are not equally spaced, but you get the idea. These are the ones that are going to be important for the standard model. As far as mass is concerned, the highest mass particles in the standard model, the top quark is the most massive at around 174 GeV. GeV, billion electron volts, okay? A proton is around 1 GeV, just for scale. So I'm not going to be very detailed. I'm not going to get bogged down in the 5-digit decimal place accuracy of what the mass of the different particles are. So to me, the mass of the top quark is around 100 GeV. 174 is around 100 by today's standards. So let's put 100 GeV up there. And then let's look at, there are also particles, I'll even put a tilde there to let you know that we're just being order of magnitude-ish. There are particles around 1 GeV. There are particles around 1 MeV. That's 1,000,000 electron volts, okay, 10 to the 6th electron volts. And then there's a huge gap, and there are some particles around 10 to the -3 electron volts. That's a little MeV, milli-electron volt. And then there's another huge gap that I won't even draw because there are other particles around 0 electron volts, massless particles, right? And then we can go through. We can go through the different possibilities. So let's do the bosons first. Why not? Okay. So we have the Higgs boson. Higgs is charge 0 and mass 125, which by my standards now is around 100. So here is the Higgs. The other massive bosons, or the W and the Z, they get their mass from the spontaneous symmetry breaking caused by the Higgs boson. So roughly speaking, they're also at that 100 GeV level. The W I'm going to put in the -1 charge column. W minus, there's also W plus, which is its antiparticle. The the Z rather, just has a single particle, the Z0. It is neutral, okay? So that's where the massive bosons are. The massless bosons, you know what those are. You have the photon, that's chargeless, 0 mass. You have the gluon, which I will call G. And you also have the graviton, which I will call H. Why do I call the graviton H? Well, there's two reasons. One is I already used G for the gluon, so H equals graviton. And why is that? Well, it's because when you think about what the graviton is, it's a oscillation, right? It's a fluctuation, a tiny little vibration in the gravitational field. The gravitational field is given by the metric tensor, G mu nu. We talked about that a little bit. And so if we're looking at a fluctuation of that, what we generally do is write the whole metric, G mu nu, as the background, and the traditional symbol for that is eta. The Greek letter eta is the flat background Minkowski space special relativity metric tensor. Then plus a perturbation, and since we've already used G, we call the perturbation H, mu nu. Okay, so it doesn't matter whether you think about H being the graviton because it's an expansion of G and H is the next letter after G, or just because we already used G in our table for the gluon. This is why. All right. Am I missing any other bosons? I think that's all the bosons. Why don't we do some fermions? Well, we have the leptons. Let me see if I can make this different color. Okay, leptons, we have the electron. That's around half an MeV. So by my standards today, that's at 1 MeV. And the electron is charged -1. And then the electron has two heavier cousins, right? It has the muon and it has the tau. And these basically go right here. There's the mu, there's the tau at around 1 GeV. And then you have the much lower mass neutrinos. Neutrinos are also leptons. There are 3 of them, and we traditionally classify them as the electron neutrino, the muon neutrino, and the tau neutrino. And roughly speaking, this is not exactly true, but roughly speaking, electronness, mu-ness, and tau-ness are separately conserved. So when a particle decays, when a particle which has no lepton number decays into, let's say the W minus, okay, it can decay into an electron and an antineutrino. It has to be a particle and an antiparticle. But the electron has charge -1, the neutrino is charge 0, so that works. But the electron has electron number +1, so the neutrino better have electron number -1, so that's an electron neutrino that you make. It would not be a muon neutrino or a tau neutrino. So the neutrinos are the ones that are around 10 to -3 eV. Again, we're being a little sloppy here because we actually haven't measured specifically what the masses are. In fact, we're being sloppy because there are 3 neutrino mass states, which are combinations of the electron neutrino, the tau neutrino, and the muon neutrino. So it gets to be very messy. Neutrinos can mix. People live their whole lives just studying neutrinos, and it's a worthy occupation to study. But for now, our study consists of writing down the symbols nu e, nu mu, and nu tau. We're not even sure what the individual masses are, so let's just group them there, roughly 10 to the -3 electron volts. Okay. And then we have quarks, right? The quarks, we have the up quark? Now the up quark, the way to remember it is, in a proton there are two ups and a down. Protons are positively charged, so it better be true that ups are positively charged. And indeed, an up quark has charge plus 2/3. And the up quark is not that much more massive than the electron. It's like less than 10 times as massive as the electron, even though the proton is 1,800 times more massive. But we talked about that. The proton gets its mass mostly from QCD, from the gluon energies inside the proton, not from the masses of its quarks. So the up quark will go over here near the electron, but in the plus 2/3 column. So that's an up quark. And then there's a charm quark at around a GeV, and the top quark way up here with the W and the Z and the Higgs of order 100 GeV. And then you have the minus 1/3 quarks, and you have the down, you have the strange, and you have the bottom quark, again around 1 GeV. And that's it. This is the standard model of particle physics, plus the graviton is stuck in there. And look, you can stare at this chart for a long time. And it's frustrating because there are clearly some patterns. There are three families or generations of particles, right? If you take the electron and its neutrino as the lightest leptons, then you have the up quark and the down quark as the lightest quarks. And then you have the next family, which is the muon and its neutrino, and the charm quark and the strange quark. And then you have another family, the tau and its neutrino, and the top quark and the bottom quark. But they're not exactly arranged perfectly here. I mean, there's this mismatch between minus 1/3 and plus 2/3 for the charges. More interestingly, the up is a little bit lighter than the down, but the charm is heavier than the strange, and the top is heavier, way heavier than the bottom. The bottom, strange, and down are comparable in mass to their charged leptons, but the neutrinos are very, very low masses, and the plus 2/3 quarks are generally heavier than the other guys. And so it doesn't really quite make much sense. There's random numbers here. It's not like these are related by the square root of 2 or something like that. So a big goal on the part of modern particle physics is to understand this pattern of particles in the standard model. We're not going to do that today, but I like to give little homework assignments for the students out there who might be watching this. Figure out this chart. Derive this chart from first principles. That would be a good homework assignment. Okay. So what are we going to do? We're going to talk about how you go from this chart to atoms. Okay, like why do some particles appear in atoms and not others? Why are the atoms made of the particles that they are? Well, what's important is particles will decay, okay? Heavy particles decay into lighter ones. That's because from a heavy particle, you can create several lighter ones. It's really the second law of thermodynamics at work. The second law says entropy increases. Roughly speaking, 4 particles can have more entropy than 1 particle can have. 1 particle can only do one thing. 4 particles can be arranged in lots of different ways. So if you can have 1 particle that can decay into 4, it will. But the question is, can it? And one point is, it has to be, more massive, otherwise you can't decay while conserving energy. The other is there can be other conserved quantities, okay? Like electric charge is the most obvious one. Whenever you're going to decay some particles, the total electric charge better be conserved. But in addition to that, you have 2 other conserved quantities I'm going to worry about. I'm not going to worry about electron number, muon number, tau number, but I will worry about baryon number. So the reason why it's called baryon number is because, remember, the quarks have color, either red, green, or blue, and you never see color in the real world. Color is confined. It's confined inside other particles. So a baryon is a collection of 3 quarks, and the 3 quarks, one of them is red, one of them is green, one of them is blue. There are also mesons. Mesons are 1 quark and 1 antiquark. So the color can be confined there because roughly, if you think of red, green, and blue as combining to make white, then the rule of quarks being confined is that the visible combinations of quarks that we see in our particle physics experiments are colorless. So red, green, and blue counts as colorless. So a 3-quark baryon, 1 red, 1 green, 1 blue, that works. That's allowed. A meson, which is a quark and an antiquark, will be red, anti-red, blue, anti-blue, whatever. That is also colorless. So those are the 2 obvious kinds of things you can make. So anyway, the reason why we talk about baryon number rather than quark number is because baryons are what we observe. Baryons are these combinations of 3 quarks, and each quark, guess what, has a baryon number of 1/3. So baryon number plus 1/3 goes to all the quarks, up, down, charm, strange, bottom, top. And then we also have lepton number for all the leptons. And the lepton number plus 1 is associated with an electron, a muon, a tau, an electron neutrino, a muon neutrino, and a tau neutrino. Okay? And this is going to be conserved, both of these quantities, electric charge, baryon number, lepton number, and of course energy. These are all conserved when these particles decay. And if you have an antiparticle of any of them, then you have baryon number minus 1/3 for an antiquark, or lepton number minus 1 for an anti-lepton. There you go. So those are the rules, okay? So we're going to talk about how particles decay. So decays. And to do that, we're going to use, before I talk about the decay, let me mention again, let me just write down here that the baryons are confined, okay, into colorless combinations. I should draw the picture because then it gets into your brain. I said the words. So either what I should say is quarks are confined. That's why I was getting confused. Quarks are confined, and gluons, okay, but the gluons just sort of go along for the ride. The quarks are confined into colorless combinations, and when there are 3 quarks, we call them a baryon. That's why I got confused. So baryons are, for example, proton will be up, up, down, and that has baryon number plus 1, because you have 3 quarks. Mesons are, let's say, up, anti-down, okay? So this is a pi plus, a pion. How do I know it's plus? Well, up is plus 2/3, anti-down is minus 1/3. There you go. This has baryon number 0, so we can make pions very easily. And you might think, well, doesn't a quark and an anti-quark, don't they just annihilate? And the answer is yes, if they were exactly the same. An up and an anti-up would annihilate very, very quickly. These guys do eventually go away, but we'll get to that. Okay. So now we can get to the decays. Now I can talk about that. So remember, the rules are heavier particles go to lighter ones, sufficiently lighter that the total mass of what you decay into is less than the total mass of the single particle that did the decaying. So the reason why energy is conserved is because the decay products have energy, have momentum. In addition to E equals mc squared, they also have kinetic energy, okay? And so the total energy, the particles that the decay products consist of, must be moving at the right velocities so that the total energy of the combination of decay products adds up to the total mass of the original particle times c squared. And lepton number, baryon number, and charge are all conserved. I said all these things out loud. Clearly I was getting excited and couldn't resist till we got to the point of writing them, but there you go. Okay, and we're going to discuss the decays in terms of Feynman diagrams, okay? So we're going to draw the Feynman diagram lines. The Higgs boson is special because it's the only spin 0 particle in the fundamental standard model chart. So it gets a dashed line. It looks like that. The fermions, all of them kind of look the same in terms of Feynman diagrams. They're just straight lines, and I will draw fermion number as the arrow there. So the arrow does not mean momentum. This arrow does not mean the direction in which the particle is moving. It means the direction in which the fermion number is flowing. So an antiparticle will have the arrow pointing the other way. And then you have the gauge bosons. And those will be wavy lines because it's kind of like light, right? Kind of like radiation, gauge bosons. So what I wanted to establish is that most of these particles just decay away, and the ones that don't go into making atoms in some complicated way. There is a rule in this game where nature, apparently Einstein once said that nature is subtle but not malicious. But you would think sometimes that nature is malicious, the way that things work out here in the standard model. It gets very, very complicated. Like every complication that you might worry about ends up actually being true in the standard model. Okay. So let's go through and figure out how things decay. And we're just going to go through all these particles and ask, can they decay or can they not, given these rules? Okay. So the Higgs can decay, certainly. In fact, it can decay in a few ways. So the Higgs couples to both fermions and to gauge bosons in ways, the Higgs itself has no conserved quantities other than energy, right? It has zero charge, zero spin, zero lepton number, zero baryon number. I was hesitating there because I was thinking of spin. Spin is also conserved, but it's part of angular momentum. So it's not conserved by itself, therefore it enters into the Fineman diagrams in a more subtle way. That's why we're not doing it explicitly. We don't need to use it for any of these purposes. So a Higgs can decay, for example, I don't know, pick whatever you want. It can decay into an electron and a positron, E+. Oops. And here's H. There you go. That's a decay. It could also decay into two quarks. So here is a quark. Let me be careful about this. Let me draw this picture a little bit bigger for reasons that will become clear. So here's a quark, here's an antiquark, and here's the Higgs. So the Higgs can decay into that. The problem is the quark and the antiquark can't just go their own way all by themselves because quarks are confined, right? So you might worry that this doesn't happen, or it just decays into a single meson, which is a quark-antiquark pair. But that can't happen because then it's one particle, the Higgs, decaying into one other particle, the meson, and that just can't happen unless those particles have exactly the same energy, which they wouldn't, which there's no meson that has exactly the energy of the Higgs. So what can possibly happen? Well, one thing that could happen is one of these quarks could give off, let's say, a Z boson, and then that can decay into an antiquark and a quark, and now you have two mesons being produced, okay? So here's how the diagrams become more complicated, because there's a million different constraints you have to satisfy when you ask how these processes actually happen. And then what you would want to do is actually calculate the rate of this happening. That might be hard. This doesn't need to be a Z. In fact, it's more likely, it could be a Z, but this is much more likely to be a gluon, right? Because gluons are strongly coupled. QCD is strongly coupled, whereas the W bosons or the Z bosons are weakly coupled. So this is a much more likely diagram. In fact, it's so likely that you should probably be including a lot more gluons in there, and it becomes very, very complicated, very, very hard to calculate. Again, full employment for professional particle physicists. And there are other ways. I'm not going to list all the possible decay modes of the Higgs, but one thing that it can do is decay into two quarks, as we said before. I should draw the little arrows like I said I would on the quark lines, on the fermion lines. So here's a quark, here's a Higgs going into a quark-antiquark pair. And what can happen is that they can spit off, let's say, photons. There's a quark, here's an antiquark, by creating a little closed loop of quark. Now, I can label that Q or anti-Q, it doesn't matter, because it's a vertical line, which means it could be either going forward in time or backward in time. If it's going backward, it's an antiquark. If it's going forward, it's a quark. And then another photon comes out here. So this is a way that the Higgs can decay into two photons. Again, you see how complicated it gets. In fact, the Higgs decaying into two photons, if I'm remembering it correctly, this is not a very common way the Higgs decays, maybe like 1% of the time, but it sticks out above the background. If we were doing a different set of videos talking about experimental particle physics, someone else would have to do them, but one of the biggest challenges is not just seeing things that you're looking for, but making sure they are really statistically significant over and above other things, other ways the same thing can happen. So, you don't ever see a Higgs boson in the Large Hadron Collider. I know that you think that we found it. What we found is the decay products of the Higgs. So we see two protons smashing into each other, a bunch of particles come out, and two of them are high-energy photons. And you say, well, what would I expect the rate of that to be in the absence of the Higgs boson existing? And I compare it to the actual rate, and I see, aha, there must be a Higgs boson there to account for that fact. Just this, I know this is going off of off schedule here, but as a function of energy. So you can look for two photons being created in the smashing of two protons together at the Large Hadron Collider, okay? And there's a bajillion ways for that to actually happen. And what you would predict is, as the energy gets higher, this is the total energy of the two photons being produced, okay? Without the Higgs, you'd expect it to be, harder and harder to make high-energy photons. There'd be some rate. So this is the rate or the total number of events that you see in your detector, okay? If you just run this for a very, very long time. But what you actually see is something like this. You see a bump. Okay, so you see what you expected plus an excess, and that excess is at the energy of the two photons equals the mass of the Higgs, 125 GeV. That's how you measure the mass of the Higgs. It's from the total energy of the photons or whatever that it turns into. Okay. There's a million complications in particle physics, so we can easily get out of hand here. But take that for granted. The Higgs decays away very quickly. 1 zeptosecond is the lifetime of the Higgs boson. For the W or the Z, you get a very similar thing. Let's just say, let's imagine you have a W minus, okay? So there, you can't just decay into two photons because two photons have total zero charge, and the W minus has charge -1. What can you do? Well, you know what you can do. You could have an electron. Let me get my arrow pointing in the right direction here. There's my electron, so that's carrying the charge. And then you went from 0 lepton number to to plus 1 lepton number. Therefore, you better make up for it by making something with 0 charge and -1 lepton number. And you know what that is? That is an electron antineutrino. There you go. And this can also happen very quickly. You can play the same game for the Z bosons, for example. All right, so where are we? Well, we have quarks. Let's look at what the heavy quarks can do. So the charm, the strange, the bottom, and the top. By heavy quarks, we mean anything other than the up and down, okay? And they can decay very, very quickly. Roughly speaking, when a heavy particle decays into lighter particles, there's a rate at which that decay happens, and there are two things that help you figure out what that rate is. One is how strongly is the coupling that makes the decay happen. So if you can decay through the strong interactions, like over here, that's why I did this gluon picture right here. This gluon would be the primary way of having this thing happen, because that's a strong interaction that happens all the time. Whereas if you need the weak interactions, like the W boson decay needs, that's a slower kind of decay. So that's one thing you need. The other thing that goes into it is how much room do you have to decay? So if you're a massive particle decaying into a set of particles with lower mass, do the total masses of the particles you're decaying into come close to what your mass was? That means you only have a tiny little window. In fact, what we say is you have a tiny amount of phase space to decay into, and that makes your decay slower. Whereas if you can decay into much later particles, then you have a lot of phase space, a lot of different ways to distribute the energies that came from your E equals mc squared into your decay products, and that lets the decay go faster. So the top quark and the bottom quark, for example, decay by very similar ways, but because the top quark is so much heavier, it will decay much, much faster. So what's a typical decay? Well, the top quark, for example, could turn into a down quark. Let's remember, top quark is charge plus 2/3. Down quark is charge minus 1/3. Okay, so the charge has to go somewhere. Plus 2/3 went to minus 1/3. Let's imagine that what happened is a W plus got made. And that W plus, well, that can decay then. And let's imagine it decays into a neutrino and a positron, the antiparticle of the electron, right, which has charge +1. Things like that. This is just one example of many, many, many. But anyway, all these quarks can decay very quickly. Likewise, the heavy leptons can decay very quickly. The mu and the tau. The mu actually can't decay that quickly. It's pretty light, and it can only decay through the weak interactions. It's for both the weakness of the interaction and the amount of phase space it has. There's not that much. It's hard for it to decay, so it leads a relatively long lifetime by the standards of elementary particles, but it can decay. So here's a mu minus, and it can decay, for example, into a neutrino, the muon neutrino. by emitting, let's see, well, it went from -1 to 0 charge, so it had better emit a charged particle like the W minus. And then guess what? The W minus can decay, for example, into an electron and an anti-neutrino. And likewise the tau decays also pretty quickly because it's heavier than the muon. Finally, so the neutrinos themselves can't decay. They can turn into each other. There's no lighter lepton, right? There's no lighter fermion than a neutrino. And since fermion number is conserved, there's nowhere for the neutrinos to go. But they can, because neutrinos mix with each other, appear to change into each other, right? A muon neutrino and a tau. Something can be created in the form of a muon neutrino and be detected in the form of a tau neutrino if conditions in between are correct. But we're going to ignore that. It's not really, the total number of neutrinos isn't changing when those decays happen. The final thing that can happen is that the quarks that do get together can get together in combinations that don't live forever, right? So mesons can decay. In fact, there are no completely stable mesons. I said, let's take the pi plus, the positively charged pion. There's a pi minus, a pi 0, a pi plus. These are the lightest mesons out there. And the pi plus is just an up quark and an anti-down, okay? That's the combination that it is. And what can happen is the down is a little bit lighter than the up, but these can come together. It's a true fact that the down is a little bit lighter than the up, but it's irrelevant to what I'm about to say. What can happen is that, in the world of Fineman diagrams, you know that the intermediate lines in Fineman diagrams represent virtual particles. So they're not real particles. So I can temporarily have them be any energy I want. It's not that energy conservation is violated. It's just they can have whatever energy I want. So I can create a virtual W boson. So I can imagine these two particles come together to make a W. It had better be a W plus, because I have a positive charge flowing through this diagram. And this W plus, virtual W plus, can have exactly the right energy to be the pion, as long as it then decays. So it can decay the way that we've seen the W plus decay over here into, let's say, an electron neutrino and a positron. There you go. So a single pion can just decay just like that into electron and neutrino. And you see that even though the pion is a strongly interacting particle, even though it's a meson, it has net baryon number 0 because of the quark and an antiquark. Likewise, its decay products here have net lepton number 0 because it's a lepton and an anti-lepton. So all the conservation laws are being perfectly well respected. So, as you see, most of these particles decay away. In fact, they decay away pretty quickly. What are we left with? Well, it's a pretty familiar story. We're left with the massless, unconfined gauge bosons. The massive gauge bosons, the W and Z's, decay. The massless gluons are confined inside hadrons. So in terms of the particles that you see massless, unconfined gauge bosons, namely the photon, gamma, and the graviton, H. Graviton, I'll remind you. I know you don't see gravitons, but you see gravity, which can be thought of as the collective force due to many, 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 many gravitons. You also get neutrinos. They're allowed to stick around. Nu E, nu mu, nu tau. You have electrons. Remember, neutrinos can turn into each other, but they don't actually decay. Electrons just sit around. There you go, E minus. Their heavier cousins do decay into them. And then you have up and down quarks confined into hadrons. In fact, hadrons, remember, hadrons are the collections of, baryons are collections of 3 particles. Hadrons, that's what I wanted to say. These combined are called hadrons. Okay. Hadrons are any collections of strongly interacting particles, namely quarks and gluons. And these are confined to hadrons. In particular, I didn't want to say hadrons, I want to say they're confined into a particular kind of hadron, light, colorless baryons. Namely, there are 2 of them, the proton, up, up, down, and the neutron, up, down, down. Okay. So these are the two that can hang around. Now, there's a subtlety, because like I said, there's a million subtleties going on here. The neutron, proton, you might say to yourself, well, wait a minute. The down is heavier than the up, and you told me that heavier particles want to decay, so shouldn't the lightest baryon be 3 up quarks? Isn't that the lightest thing that you can make? There are particles made of 3 up quarks. There are delta baryons, okay? But remember the Pauli exclusion principle. You can't have 2 particles in the same state, and so if I have 2 ups and a down, their wave functions can be the same because they're different kinds of particles. They're not identical particles. An up and a down are not identical, but 2 up quarks are identical. So it turns out, I'm skipping some steps, but it turns out if you try to squeeze 3 up quarks into the same baryon, you can do it, but only by having them be a little bit more energetic than they otherwise would be. In particular, their spins have to be pointing in the same direction. So it costs a little bit more energy. You get a slightly heavier particle. So the masses of baryons are not just the sums of the masses of the quarks they're made out of. It turns out in the real world, the lightest baryon is the proton with 2 ups and a down. But what about 2 downs and an up? I mean, that's not the lightest baryon. Neutrons are heavier than protons, so shouldn't they decay? And the answer is yes, neutrons do decay. And then your question is, well, why do we see neutrons all over the place? Why do we live in a world which is, literally the Earth? Or I'm pretty sure that your body, most of its mass is in the form of neutrons, not in the form of protons or electrons. Why is that? Well, let's first explain how they decay. A neutron, N0, is an up, a down, and another down. Okay, it's a collection of those 3 quarks. And the way it decays is that one of those downs turns into an up, okay, which we know can happen via the W bosons. So you just imagine this, this, this. Here are your particles, your quarks, carrying their fermion number. But the down, which is charge minus 1/3, emits a W minus to become an up quark. And now you have 2 ups and a down, and this is called a proton. And the W minus does its thing. It turns into an electron antineutrino. There you go. So this can happen, absolutely. Neutrons do decay, but here's the thing. The total mass of proton plus electron plus neutrino is less than the mass of the neutron, but not by much. So you go to the details here. Let me see. I looked it up. I don't remember these things. The mass of the neutron minus the mass of the proton plus the mass of the electron plus the mass of the neutrino divided by the mass of the neutron is about 0.1%. It's a tiny number. So the phase space for a neutron to decay is very tiny, and the decay happens via the W boson, which is a weakly interacting particle, so the decay is very slow. So the lifetime tau neutron, again, I don't know the exact numbers, but it's about 10 minutes, which is very short on the timescale of the age of the universe, but hugely long on the timescale of most elementary particles. The Higgs boson decays in a zeptosecond, remember? So that's because of this conspiracy where the neutron is just a little bit heavier than the proton. So neutrons can live a long time. Again, cosmologically speaking, that's not a long time, but that's why you can find neutrons out there in the world. And before going on, so the thing that we'll go on to is to say that once you can combine neutrons with protons, then they can live forever in the right circumstances. So you can have neutrons more than 10 minutes past the birth of the universe, okay? But what I want to mention is that, this is a weird fine-tuning in the laws of nature. I'm not going to say that God did it, because I don't believe that's true, but I'm not going to hide from the fact that in the standard model of particle physics, there are some weird coincidences going on, and these weird coincidences seem to us to help us exist. There's some other weird coincidences that have nothing to do with our existence, so don't make too much of it. But what if the masses of the particles were just slightly different, or the interaction strengths were just slightly different, so that the mass of the proton was greater than the mass of the neutron? Right now, the mass of the neutron is a little bit bigger than the mass of the proton. What if it were the other way around? It's very easy to imagine jiggling with the masses of the quarks to make this happen. okay? Because we have no principle from which to derive the masses of the quarks, so we can easily imagine a universe in which neutrons were a little bit lighter. So in that case, protons would decay into neutrons, because protons would be heavier. If the protons were, enough heavier, they could spit out a positron and turn to a neutron, then that would happen. And the positrons that were created by decaying protons would annihilate eventually with any electrons that were out there, and then you'd be left with a world of neutrons. There would be no protons around. So because neutrons are a little bit heavier than protons, you end up with a world where there are both protons and electrons, and then complicated things happen to make sure there are some neutrons lying around also. But at least there are two different kinds of particles, protons and electrons, that have electromagnetic interactions. And that's, as we're going to say soon, that's what makes the world an interesting place. If neutrons were lighter than protons, you would have no charged particles lying around. You would just have neutrons. And then the question becomes, can you make stars? Can you make life? Can you make anything interesting in a world that is just made of neutrons? And the answer might be no. But I don't know for sure. Like, you can't make life as we know it if the world were nothing but neutrons. But could you make other things that I cannot quite conceive of because my brain is too tiny and I don't have the ability to envision what life would be like in a world with nothing but neutrons? I don't know. It's interesting and worth thinking about. But this is a feature of the world, is that the proton is a little bit lighter than the neutron, and thank goodness for us being here. Okay. In the real world, this is the fake world, the world of neutrons. In the real world, neutrons can be stable if they're inside certain kinds of atomic nuclei. So stable, I mean never decays. Nuclei are just collections of neutrons and protons stuck together. It's basically, we're not going to go into this, but again, another whole area of physics that many, many people devote their lives to is nuclear physics, right? All we've said is that protons and neutrons are made of quarks, and that the quarks inside the protons and neutrons are held together by gluons. But what that leaves is a little bit of extra force that can actually stick protons and neutrons together. So it's much like, even though atoms are neutral, even though two hydrogen atoms are neutral, you might say, well, they're electrically neutral, there's no force between them. But actually there's a tiny force between them, because there's a little leftover remnant force the two hydrogen atoms want to come together, as we'll discuss in just a second. Likewise, even though a neutron and a proton are colorless, there's still a little bit of remnant nuclear force that wants them to come together. In fact, it's pretty strong as it works out, so that's how you can make atomic nuclei. So, for example, the deuteron. Here's an example of a deuteron, which is one proton and one neutron stuck together. You can never accurately draw this. Deuterons are actually very, very close to spherical. The neutron and the proton are sitting right on top of each other in the deuteron. They're not like, here's the proton and here's the neutron in some dumbbell shape, okay? But it's hard to draw that, so you always draw it this way. It's the deuteron. It's an isotope of hydrogen. I'm not going to remind you of all the chemistry in the world, but we classify nuclei by the number of protons. And so this has one proton in it, so this is a kind of hydrogen, the deuteron. And you can figure out, you can actually go either measure it or do ab initio calculations in nuclear physics, and you find that the mass of the deuteron is, I got to look this up, 1875.6 MeV. Okay? Close to twice the mass of the proton, or twice the mass of the neutron, but not exactly. And then you can say, well, can it decay? Right? This is the game that we play. Say, like, well, can the neutron in that proton, in that deuteron, decay? Well, it would decay into a proton, presumably, and then you have two protons, and two protons cannot stick together. That's a lot more energy than just two protons individually, because they have electromagnetic repulsion. The strong nuclear force would like them to come together, but two protons without any neutrons hanging around, the strong nuclear force loses that battle, and the electromagnetic force pushes them apart. So that neutron has to decay into a proton, and that proton has to go its own way, so they have to be separate. So you compare the mass of the deuteron to the mass of a proton plus what the neutron decays into. A proton plus an electron plus an antineutrino, and that works out to be 1877.1 MeV. So in order for the deuteron to decay, it would have to decay into particles that are heavier than it is, which means it doesn't happen, which means the deuteron is stable. That's why, and you want to say, well, why is the mass of the deuteron that? That's too complicated. That's above our pay grade for these videos, but it's the combination of many, many things going on inside the deuteron, the strong nuclear force, the weak nuclear force, the masses of the quarks, the whole shebang. The point is that under these circumstances, and in heavier nuclei as well, the deuteron can in fact be stable. And in fact, logic like that leads you to all the isotopes. All the isotopes in the periodic table of the elements, right? So what we care about here, the periodic table is what you care about if you're a chemist, because the periodic table, the columns in the table are telling you something about the chemical properties of the atoms. But if you're just dealing with the nuclear physics, it's the isotopes that matter to you, not the individual chemical elements. And it turns out, again, I had to look this up, how many stable isotopes are there, would you guess? Do you know? Any nuclear physicists out there in the audience? There are about 250 stable, and I'll put stable in quotes, isotopes. And that's because, why is stable in quotes? Because, this is a really close battle, as you see from, the closeness of these two numbers for the deuteron and its purported decay products. On the one hand, when you try to make a nucleus, you're already fighting against the fact that protons are positively charged and neutrons are neutral. So there's no negatively charged particles in the nucleus. So there's a repulsion. Like charges repel. Protons do not want to be brought close to each other. That's why nuclear fusion is hard and why we do not have effective, cheap fusion energy powering our reactors, okay? Because getting the protons close to each other is very, very difficult. On the other hand, you have the fact that if it works, the mass can be a little bit lower, so they want to be there. So they want to be there, but there's a barrier. That's why nuclear fusion is hard. And when I say they want to be there, it's not by a lot. Like the deuteron is not that difficult to break apart. A strong gamma ray hitting a deuteron can just break it apart pretty easily. So there's this combination where the strong nuclear force wants the baryons to come together, the electromagnetic repulsion pushes them apart. You need some neutrons in there because neutrons will give you some extra strong nuclear force, but too many neutrons will just decay because neutrons want to decay. So there's all this combination, this complicated combination of forces counteracting each other. And that's why, it's complicated to do nuclear physics. And the reason why, to finally finish this sentence, the reason why it's 250 stable nuclei is there are 250 isotopes that, as far as we know, would never decay in an observable amount of time. Okay? We think, though, that only 80 of them or so are truly stable. So, by which we mean there's another, 170, which will linger around for many, 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 many years and then eventually decay. That is what we think will actually happen. Anyway, this is the reason why I'm doing this is because these are the low energy allowed stable particles in the standard model of particle physics. So what we're left with is, I said what we're left with is this stuff, right? But then we had to go into some details about how the baryons get together. So the world of you and me and the tables and the sun and the moon and the stars is made of electrons, around 250 stable isotopes, neutrinos, they exist, they're out there, but they pass right through you, right? You probably heard this fact, like a neutrino that it comes out of the sun will probably pass right through the entire Earth without ever being stopped because its weak nuclear interaction is so weak. So even though neutrinos are there, they don't affect our lives very much. And so let's get down to the physics of our everyday lives, literally the table and chairs and our biology and things like that. So forget about the neutrinos. Forget them. And then you have, this is the matter of the world. And then you have the forces, which are electromagnetism, right, photons, and gravity. And those are the forces. And that's it. That's the world. This is the world, again, that you and I are made out of. We're leaving some bits out in this very, very simplified discussion because we're basically, what we're leaving out is the weak nuclear force and the neutrinos, because they're very rare and they don't have a lot to do with what we care about. Everything else that you would make from the standard model either decays away very quickly or interacts with us very, very weakly. So we don't need to worry about it. So it's interesting that this is sort of the leftover low-energy remnants of the standard model of particle physics. And it's a complicated story to get there that we just raced through at incredibly high speed. But everything in the world that you encounter in your everyday life, unless you're a working physicist, is made of this stuff. So, not just tables and chairs. Volcanoes and hurricanes and bacteria and plants and people, psychology, art, literature, music, sound and light. It's all some combination of this stuff in interesting ways. Of course, the ways are very, very interesting. And if someone said, write a sonnet or write a symphony, you would not start with the standard model of particle physics and try to derive it from first principles. That'll be another video that we'll talk about. But these are the ingredients. This is all you need. And that's kind of amazing. I'll name one more fact. I want to talk about mostly some putting these together now to get atoms and so forth. But an extra fact is there's an asymmetry, an imbalance between matter and antimatter. Famous fact, right? There's more matter in the universe than antimatter. In fact, we don't even know that for sure. It's really a symmetry in baryon number that we know about. So we know that in the observable universe, there's a lot more baryon number than antibaryon number. Why not? Because when you say matter and antimatter, you mean something like lepton number plus baryon number is matter, anti-lepton number and anti-baryon number is antimatter. We know the baryon number of the universe because baryons are protons and neutrons, and they're very easy to notice. We can find them fairly easily. But lepton number and anti-lepton number can be hidden in neutrinos. And the total number of neutrinos in the universe is very hard to count. So what we know is that in the charged particles, and in the strongly nuclear force interacting particles, there's a big imbalance between matter and antimatter. But maybe it's made up for in the neutrinos. That we don't know. But there's certainly an imbalance in baryon number. We don't know why. So there's two possibilities, and one of them is not very plausible. One possibility is that somehow the universe was born with a slight imbalance between baryon number and antibaryon number. That's hard to imagine it being true. You have to do it in exactly the right way, because baryon number, even in the standard model, is not 100% super-duper conserved. Under the right circumstances, it can vary. But also, it just seemed weird. Like, why should there be an imbalance? The other is exactly because we can imagine processes that do violate baryon number. It's, again, full employment for theoretical physicists to invent what we call baryogenesis schemes. Schemes where in the early universe, as it expands and cools, there are particles that decay and interact with each other, which end up producing a few more baryons than antibaryons. You can run the numbers. What you need in the very early universe is, at very early times, when temperatures were much higher than the mass of the proton, there were a lot of both baryons and antibaryons. And most of them decay away. Most of them annihilate with each other, turn into photons or something like that as the universe expands and cools. What you need is, roughly speaking, if I'm going to get the number right, for every 10 billion antibaryons, you need to have 10 billion and 1 baryons at very, very early times. So all but one of every 10 billion baryons and antibaryons annihilate away, and you're left with the tiny little remnant, which makes up all of the stuff that we see today. So I'm not going to talk about that, but that is something that you need. You need to understand why all these particles, why there's this imbalance there. We don't really know. Okay. So here, now we're going to reach sort of the punchline of really what I wanted to talk about. So these are our ingredients for the physics of everyday life. Electrons, stable nuclear isotopes, electromagnetism, and gravity. Okay. The weak nuclear force is too weak. The strong nuclear force is only in the isotopes. Don't need to worry about those. The Higgs boson is far too weak. The heavier fermions decay away. This is what we're left with. So there's only two kinds of matter. right? Nuclei and electrons. And there's only two forces, two big long-range forces that are important in the everyday world. So think about those forces just a little bit. There are only two of them. And one of them is gravity. And gravity, I'm going to hate to say this, but gravity is dumb. I don't mean that it's dumb to think about gravity or to care about it. I just mean that how gravity acts on the world is simple. It pulls things together. There's slight complications if you talk about dark energy or something like that, or inflation in the early universe. But again, we're trying to understand the everyday world. We're trying to understand what's happening right here, right now, in the room that you're in, okay? So the pen falls toward the earth. That's all that ever happens with gravity. It just tracks things together with an inverse square law. It's incredibly simple, okay? Whereas electromagnetism is interesting. Let's say it's clever. I just made that up right now, but I think it's true. And the reason why, you know the reason why, because when we talked about gravity, we talked about the principle of equivalence, right? All particles fall at the same rate in a gravitational field. Not only is all the gravity does is pull things together, it pulls everything together in exactly the same way. Whereas E&M, electromagnetism, acts on you differently depending on if you're positively charged, negatively charged, or neutral. So E&M can both push and pull. It pulls things together if they have opposite charges. It pushes them apart if they have the same charge. So what that means is what electromagnetism can do has an infinitely greater variety than what gravity can do. Because, gravity, you might think it's just like, gravity does one thing and electromagnetism does two things, so how much more important can it be? But you can balance, you can play them off against each other, and in fact the world does that. And the entire reason the world is interesting can ultimately come down to the fact that electromagnetism is clever because there are positive and negative charges in the world. So this explains, this accounts for electricity. All of electricity comes down to this fact. Electricity comes about because, you have these atoms. We'll talk about atoms in a second, but atoms are these heavy nuclei and very light electrons, and the electrons can be pushed around because they're much lighter than the nuclei, and they're charged, so they can be pushed around by electromagnetic fields. So if you just gather together a bunch of electrons, so you have minus charges on one side of something, and then combine a bunch of positive charges on the other side, put protons over here, okay. Then if you put an electron in between, it's going to zoom over to the positive charges, and we call that electricity, okay. So in the very, very likely condition that you are currently watching this on an electronic device, you should thank your lucky stars that there are positive and negative charges in the world, because that's what lets us manipulate the electrons going through that device to create electronics and electricity. Okay? It's ultimately because of this feature of the standard model of particle physics. The other thing this explains is chemistry. You can tell that we're not going to go into details in any of these higher level concepts, but I want to connect them to the underlying world beneath. Chemistry is, again, there's a push and a pull, but in this case it's a little bit more subtle. I mean, electricity is very subtle also. Like once you get into superconductivity and all this stuff, extremely subtle, or even circuit boards for that matter. But I want to talk about the subtlety in chemistry because it harkens back to our discussion of the Pauli exclusion principle, right? So just think about, e.g., a hydrogen molecule. So a hydrogen molecule, just two hydrogen atoms. So the point is that, let me draw it this way. Ooh, it's not very good, but okay. There's a proton, another proton. And in this cloud are two electrons. Okay. The point is that around one hydrogen atom, you could imagine, you can put one electron, no problem, around one nucleus. There's still room for one more electron in there, as we'll discuss in a second. So in a sense, there want to be two electrons hugging that single proton. but there's not enough electric charge to make that happen, right? Once you have the proton and one electron, it's done attracting things, roughly speaking. But if you have two hydrogen atoms, they're happiest. The electrons sort of want to combine. The electrons want to both be hugging either one of those protons, so they want to pull them together. But, of course, then the protons begin to push things apart, right? The protons have a positive electric charge. And, there's also the Pauli exclusion principle, so you have to have the electrons lined up in the right way. And what you get at the end of the day is you can have a potential energy. And this R here is the distance between the two protons, okay? So you can say, what are the forces acting on the protons? If they're very close together, the protons push each other apart, okay? There's electrons, but the electrons are all spread out around them, so they're not going to help that much in ameliorating the electric repulsion between the protons. So it costs energy to go very close by, but also if they're far away, they want to be a little bit closer. So what you get at the end of the day is a curve that looks like this, which says this is the potential energy between the two protons, and there's a favorite place to live. There's a favorite distance to have between those two things. And it's all because of some complex interplay of electromagnetism and the Pauli exclusion principle. Okay? And so this is why you can get molecules sticking together, why you can get two atoms that want to come together. Okay? It's, again, ultimately because of quantum field theory and gauge theory and other things like that. They wouldn't have told you that in your chemistry class, but chemistry is just applied electromagnetism in a world that has the Pauli exclusion principle in it. So let's actually let's talk about that in a little bit more detail. Let's finally get to atoms. We're like more than an hour in to the video, and we're finally getting to the title, atoms. So we have, of course, hydrogen atoms, which is just one proton plus one electron. It's the simplest one. There can be isotopes, there can be ions, all that stuff. We're not going to get into that. But basically, it's the simple thing. The electrons have wave functions, as we discussed before, but you know what hydrogen is about. Helium, okay. So by the way, for hydrogen, if you have a deuteron instead of a proton, so if you have the combination of the neutron and a proton, you get basically the same hydrogen atom. You get what we call deuterium, but chemically it's the same. It's the electron that is doing all the chemistry. This is the point of this little monologue up here, is that the electrons are doing the work in chemistry. The protons are being pushed and pulled, but it's the electrons that are doing the pushing and the pulling. The protons interacting themselves are just going along for the ride. So, so hydrogen with a deuterium in the middle, with a deuteron in the middle instead of just a proton, is pretty similar. A little bit heavier, heavy water, right? Heavy hydrogen. Helium, two protons, two neutrons, two electrons. And something is already happening, interesting, with helium because of physics, because of the Pauli exclusion principle, right? So the Pauli exclusion principle, remember, says that two identical particles cannot be in exactly the same quantum state, okay? So if you have a helium nucleus, this is our little helium nucleus, two protons, two neutrons, and I'm just going to do this terrible sort of Rutherford atom kind of picture that is not right, but it gets the point across. Two electrons like that, okay? Really, the electrons have wave functions. Really, the electrons want to be in the lowest energy wave function they can be in, but they can't be in exactly the same wave function because that would violate the Pauli exclusion principle because electrons are indistinguishable particles, okay? Happily for life and for chemistry, Pauli exclusion principle, no two identical particles can be in exact same state. Happily, electrons have spin. Okay, so these two electrons have two spins, and all you need to do to put them in the same shape of the wave function is to let the spins be oppositely aligned. one spin up and one spin down, or as you know from our explorations of entanglement, you could say spin right and spin left, but they're oppositely aligned. They're entangled with each other in opposite directions. So the electrons in helium have opposite spins. So you can put two electrons with wave functions that have the same shape as long as their spin wave functions are different. That is satisfying the exclusion principle, okay? But then you're done. In terms of this thing that electrons can do, you can't put a third electron in there doing the same thing because there's only two values for spin up and spin down. You've used it up. The electron is a spin 1/2 particle, okay? So now this is the origin of why helium is a noble gas, why helium does not interact, why there are not helium molecules. The helium has its electrons filling the thing that they can fill. Those two electrons are in their lowest energy state, the lowest energy shell, as we would call it, and that's all you can fit there. There's no more room for interesting chemistry. The electrons don't want to be in someone else's orbit or anything like that, like the hydrogen atom did. The helium electrons are perfectly happy where they are. So helium is, roughly speaking, non-interacting chemically. But we can keep going. What's the next one? Beryllium. 3 beryllium. 3 for 3 protons, atomic number 3, okay? In fact, I'm not going to do, believe me, I'm not going to do the whole periodic table of the elements. From beryllium up to neon, okay, this is filling the next shell of electrons. And we can actually roughly appreciate why that's true. You know, now I've been previously apologizing to mathematicians and to particle physicists. Now I will apologize to any chemists in the audience, because we're not going to do justice to all the complications here, but roughly we can understand why this makes sense. The point is that when we did electron wave functions, right, the electron wants to be close to the proton, and so what we can do is to plot as a function of distance from the proton, we can plot the electron wave function psi, and the lowest energy one looks roughly like this, okay? And that's both of the helium electrons are going to be doing that in space. Psi is a function of r. So what's next? What is the next highest energy thing? Because we cannot put any more electrons in that lowest energy level. And it turns out there are two different things that you can do. So what you might guess is that you can sort of let the thing, what should I say? I'll just tell you the answer and then I'll back up and justify it, okay? Here's the answer. What I will plot here is a wave function that actually looks like it shouldn't be the next highest one. And then I will separately plot over here a different thing, but instead of r, which is just the distance from the center, I will write x, because what I mean is the specific direction in space, x. And then I will plot what you probably were expecting. So this is a wave function here that only crosses 0 once. The yellow one over here crosses it twice. And so what you're thinking is, well, it costs energy for a wave function to change, for a wave function to have a gradient, okay? So when an electron wants to be in its lowest energy orbital, it wants to change as gradually as possible, its wave function. So that's clearly what the white one does. It changes very, very smoothly. The green one changes a little bit more. The yellow one changes a little bit faster. And as you go up and up and up in energy, you'll get more and more wiggles in the wave function. That makes perfect sense. But it turns out that the yellow and the green are of approximately equal energy. And the reason why is because, the same reason why I wrote r over here and x over here, this yellow wave function is symmetric. You notice that as if you send r goes to minus r, it looks exactly the same. And in fact, it can be spherically symmetric. So it can vary in the r direction, but there's no variation going on in the x, y, or z directions. It's a perfectly spherically symmetric thing. Whereas this green one over here changes sign as you go from left to right. So it can't be spherically symmetric. And very roughly speaking, if you've ever seen the pictures of, the nucleus and then different electron orbitals. So there's an orbital. These orbitals look like this. And if I can do it correctly, well, I can't do it correctly here, but it's spherically symmetric. That's all I want to get across. Whereas these orbitals, you've seen pictures that look like this, where they're like p orbitals. Oops, that's not the one I wanted. They look like they're double-lobed, okay? And guess what? They can be double-lobed in 3 different directions. So if I count how many ways, so there are 2 orbitals like this, 2 states. Why? Because there are 2 spins, only 1 spatial wave function, but 2 different spin alignments. Here, there are 3 different orbital wave functions. One with the 2 lobes in the x direction, y direction, and z direction. And then there are 2 spins for each of them. So there are 6 states for this. So there are a total of 8 states for the electrons in these next level orbitals. So what I hope is that the numbers work out correctly. So I said that hydrogen is 1, helium has 2 electrons, and this next shell goes from beryllium to neon. So that's from 3 to 10 inclusive. So that's 8 different elements. And exactly is what we got, the 8 states there, okay? So all of this is a very, very fancy way of saying that all that stuff you learn in chemistry is ultimately because of features of particle physics in some sense. Now, you don't need to know all these features of particle physics. Typically in high school, people take chemistry before they take quantum mechanics, but there is some relationship there. It's not completely separate, okay? And from there, you just keep going. You just make things more and more complicated. And there's a complicated story of how the different electron orbitals get filled, etc. And that's the life of a chemist. So just to show you one example, carbon, which has 6 protons. So if the 6 protons have 6 electrons attracted to them, 2 of those electrons will be in this lowermost helium-like orbit, or hydrogen-like if you want, and then 4 of them will be in the next shell, the next set of orbitals. And so if you have 4 of these 8 are filled, so you have 4 filled electron states in the orbitals and 4 open for business. And that's why carbon is interesting. That's why carbon is the backbone of life, because it has the most number of interesting things going on. It has split its electrons. It has 4 electrons to play with, and it has 4 electrons it can take, so it's sort of maximally interactive. So you end up doing what is called organic chemistry, okay? So you have, carbon atoms sticking to each other, and then also other atoms. So typically the simplest thing in the world is to put hydrogen atoms everywhere, right, to get hydrocarbons. But you can do other things. You can put like an oxygen atom, and if you go through the little thing that we did there, oxygen has 2 open slots, and you can finish that. So that's a nice little example. In fact, this is a very famous molecule that you could look up of an organic chemistry molecule. We're not going to do organic chemistry in any detail. We're not going to do chemistry in detail. We're done with chemistry. That's what I wanted to tell you about chemistry. What I wanted to tell you about chemistry is it all comes down to electromagnetism and the Pauli exclusion principle. It's all just an application of that. Okay. One final thing, one final thought before I let you go for this video here. And the final thought is, I'm going to write it down very explicitly here because this gets very easily misinterpreted. If quantum field theory is basically correct, we never know, right? Quantum field theory is by far and away the best currently applicable theory we have explaining the world at a fundamental level. It might not be completely correct. In fact, what we know about quantum gravity suggests the quantum field theory is not completely correct. But quantum gravity is very far away from our experimental reach. So again, if we're trying to explain the world of the everyday, then quantum field theory seems to be a good way of doing it. Then we will never... It's very hard to say never in physics, but this is a conditional sentence. If quantum field theory is correct, then we will never discover new particles or forces relevant to everyday physics. What do I mean by this? By everyday physics, I mean the stuff that you literally see around you right now. Given that I'm presuming you are not working at a particle accelerator or a telescope or anything like that, the stuff that you're touching, okay, the stuff that you're made of yourself, everything you're visibly seeing with your eyes or touching with your fingers, that's everyday physics. The physics of tables and chairs, planets and stars, stuff like that. Okay, we know what that stuff is made of. It's made of the list that I showed you before: the electrons, the isotopes, electromagnetism, and gravity. That's what you need. If you want to extend your definition of everyday physics to include, why the sun shines, for example, okay, we can put the nuclear forces in there. That's fine. We need neutrinos to make the sun work, etc. But it's still within the standard model of particle physics. And the claim here is that in terms of that, in that very, very narrowly prescribed area, everyday physics, we're done. We have discovered the fundamental ingredients. We're not going to find anything new. Now, of course, we're going to find new physics more broadly. Like, we don't know what the dark matter is, right? We don't know why there's an imbalance between baryons and antibaryons in the world. There's plenty of things we don't understand. We certainly don't understand quantum gravity or the origin of the universe or things like that. Physics is not done. But everyday physics has its complete set of ingredients. So I don't even want to say everyday physics is done, because the way those ingredients combine is very complicated. We don't understand it, right? We don't understand superconductivity, for example. There's plenty about chemistry or biology that we don't understand, if you haven't noticed, right? So I'm not saying that all of those things are understood. I'm saying we know what the ingredients are. I'm saying that whatever the explanation for high-temperature superconductivity or for biology turns out to be the origin of life, it will not involve ingredients from fundamental physics over and above the ones we've discussed here. And the reason why is because if there were new particles and forces, and quantum field theory describes them, then we would have discovered them. So there's a symmetry of quantum field theory called crossing symmetry. And I think that I mentioned this in passing, but maybe didn't give it this name. Crossing symmetry says that if you have a Feynman diagram describing some interaction between particles, and it has a certain strength. So let's imagine there is, here's an electron, and this is an electron, in your brain. Okay, it's part of you, part of your consciousness, right? And someone says, well, I think that there's another particle called the X particle, and it interacts through some new force, call it the Y force, with electrons. And that understanding this new force is crucially important to understanding consciousness or the origin of life or why tables are solid or something like that, okay? That's a perfectly legitimate hypothesis. You can think that. You can suggest it. You could investigate it. But we have a Feynman diagram, and so we can calculate the strength of this interaction. How likely is it that an X particle will interact with an electron? And crossing symmetry says I can take that diagram and I can rotate it by 90 degrees. And I get another diagram which has the same strength, which is just as noticeable as this diagram is. And when I do that rotation, of course, particles become antiparticles if they go from one side of the diagram to the other. So this is saying that I could take an electron and a positron, E minus and E plus, and I can smash them together to make a Y boson, which will then decay into two X bosons, or an X and an anti-X boson. And we've done that. This is what we do. This is what particle physicists love to do, smash particles together and look to see what comes out. So we have very strong constraints on where particles are. We know there are certain kinds of particles you can imagine existing that definitely don't exist. So there's no question, again, if quantum field theory is right. If quantum field theory is not right, all bets are off. But that was the presupposition of the argument. Of course, there are particles and forces we haven't found yet. But we know that because we haven't found them yet, they're either particles that are too massive to be created, okay, in collisions like this, up to Large Hadron Collider scales, or they're too weakly interacting to be created. So this diagram, maybe it exists, but the actual numbers attached to it are just incredibly tiny. Or the particles just decay away so fast that even if they're made, you don't notice that they were made. In any one of those cases, there's no way for this new particle and force to have any impact on our everyday lives, unless your everyday life is that of a theoretical or experimental physicist, okay? And this fact, sometimes I state it, if you read my book, The Big Picture, I go into this fact and I try to explain it. I say the laws of physics underlying everyday life are completely known. All the words in that sentence matter, okay? It's underlying everyday life. It's not all the emergent laws of higher levels. I'm not saying we understand economics, okay? But I understand the electrons and the nuclei that economists are made out of. And they're completely known in the realm of everyday life, not in the realm of the universe. I'm not saying we know where the universe came from, I'm not saying that physics is done. I'm a physicist. How could I ever say that physics is done? I would do something different if I thought the physics was done. But the laws of physics underlying everyday life are completely known. And this fact is reflected in technological advances, okay? We sometimes think that, doing work in fundamental physics is crucially important for technological advances, and it is, but only because we need technological advances to do fundamental physics. And therefore, the drive to do fundamental physics leads to new technological breakthroughs. But the technological breakthroughs themselves do not involve new fundamental physics. The last time new fundamental physics, new particles or forces, turned out to be relevant to technology was probably the 1950s. The top quark and the Higgs boson, these things are not things that affect technology in any way, because you need $1 billion accelerator to make them, and then they decay away in 10 to the minus 20 some seconds, okay? And that's going to continue to be true. There will be plenty of technological advances, but the technological advances will consist of clever ways of arranging these ingredients: electrons, isotopes, electromagnetism, and gravity. And that gives us constraints on what we can do. Again, if quantum field theory is correct, it means that you can't bend spoons with your mind. I cannot bend this pencil just by thinking about it, other than having my mind, say that my arm should go there and bend it. But there's no way that a force can be extended from my brain, because the only forces that go over large distances are electromagnetism and gravity, okay? It means that tractor beams will be difficult to construct. Not necessarily impossible, but you'd have to do them out of electromagnetism. There's no new forces. Shields that you can put up around your spaceship to protect you from laser beams, well, if you can do that with electromagnetism, that's great. Gravity is too crude. Gravity is dumb, right? Electromagnetism, maybe you can do it, but there's no other forces, no other particles that will be relevant to this. Sorry about that, but it's our job here not only to discover cool new things about the world, but to face up to them, to accept what the world is teaching us. So there's both a frontier of moving beyond everyday physics, the Big Bang, quantum gravity, dark matter, etc. And there's another frontier of how these ingredients come together to form everyday physics: statistical mechanics, chemistry, biology, psychology, all that stuff. There's plenty more science to be done, but we should also kind of recognize that some of the science we wanted to do, we actually have done.